Hello, my name is Michael Curry. I'm a designer and desktop fabrication specialist based in Kansas City, Missouri. I created this webinar with the Ultimaker team to show you how SolidWorks users like me export jobs for desktop 3D printing. In this session, we will cover a few best practices for delivering your SolidWorks parts to a desktop 3D printer, with a specific focus on the file formats for exporting multi-part and multi-material designs so that they can be used with a multi-material desktop 3D printer. The primary focus of this talk is to discuss the two file types available for moving designs from SolidWorks to Cura, how they differ from each other, and what capabilities they offer. We will also introduce you to two new tools in Ultimaker Cura that integrate desktop 3D printing directly into the SolidWorks ecosystem, making it even easier for you to deliver your designs to your 3D printer without creating an export file. We will be using SolidWorks 2018, Ultimaker Cura 3, and an Ultimaker 3 desktop 3D printer. We are going to demonstrate the process of exporting designs from SolidWorks into Cura by looking at two different design study models. One that simulates a simple overmolded part, and the other that simulates a complex working part. But first, I'd like to offer some dessert before the main course. SolidWorks users are important to the Ultimaker team, in part because they use SolidWorks to design their 3D printers, and thus appreciate how helpful time-saving tweaks can be. So when the team had the opportunity to roll out a major update to the Ultimaker Cura platform, they bundled in two software plugins for SolidWorks users to allow them to cut out the export file stage entirely and open their designs right in the 3D printing setup tool where they can prepare their jobs. One small warning: these tools don't entirely replace the export best practices shared elsewhere in this webinar, and they can only be used on systems that have SolidWorks 2016 or later already natively installed, which means you can only use this on Windows operating systems with SolidWorks successfully installed and activated. I suggest that you see these integration plugins as a means to accelerate more typical print from SolidWorks scenarios, using standard settings in your installed SolidWorks software to save you time. For the serious SolidWorks user looking to have all tools possible at their disposal for export, you want to stick around for the entire webinar to master the underlying concepts, technologies, and settings for these times when plugins just won't work. First, we'll install the Cura SolidWorks plugin. In the Plugins menu, select Browse Plugins. Scroll down to SolidWorks Integration and choose Download. After a quick close and reload, you'll now be able to open SolidWorks parts and assemblies directly inside Ultimaker Cura. Going to the Extensions menu, there are two items under the SolidWorks Integration heading. First, Configure, which allows you to specify whether Cura should use coarse or fine export templates when importing your SolidWorks parts. You can also pick Ask Me Every Time, if you're the kind of person who likes to keep your options open. The second item is a step-by-step tutorial on how to set up a custom macro within SolidWorks itself. When properly set up, the macro will offer a Send to Cura option right on your toolbar. The process is pretty quick, and given that all the steps are included underneath this button, I won't waste your time by going over them in detail right now. So now you have two means to work with SolidWorks parts and assemblies right in Cura, cutting out the export file process entirely. As I mentioned before, under the hood, all the typical export and import stages still take place when you're using the SolidWorks integration tools. So stick around to learn a bit more about that process, as well as the best practices for your multi-part and multi-material projects. The first design study we will look at is a simulated overmolded part. We want to print this part using two different colors of PLA plastic. The first color, blue PLA, will represent the underlying structural base, and the second color, pearl white PLA, will represent the overmolded surface. When using desktop multi-material printing, each of the materials in the model needs to be represented as a separate body. So in this case, we'll have two bodies, the blue core and the pearl white covering. For the interface of these two materials, I have found that a simple zero allowance surface-to-surface condition will provide excellent adhesion. You may find in your own experience that some materials need to be printed with an overlap condition to ensure they're firmly keyed together. This can be done by insetting one material into the other by a few fractions of a millimeter. With the parts designed, it's time to export them. And now we get to the meat of the issue. There are two file formats available to move an object from SolidWorks into Cura: STL and 3MF. First, we're going to look at the STL format and walk through the process of exporting and printing our overmolding study using it. STL, short for stereolithography, is the oldest and most universally supported file type of 3D printing. Dating back to 1987, STL files were originally created to support early stereolithography-style 3D printers. An STL file's basic units are triangles. When you save an STL, the surface of your objects is described as a series of triangles, listed out as a set of points in three-dimensional space. There are a few different types of STL file, but the two most important to remember are ASCII and binary. An ASCII STL file lists out the points of each triangle in 3D space with three values, x, y, and z, for each point. Plus, there is a fourth point, a value that indicates which side of the triangle is facing out. This last value is important because each face of an STL is only visible from one direction, and your 3D printer uses this visibility to determine what's the inside and outside of your model. So if this value, known as the normal, is inverted, it will cause errors. You'll often find inverted normal faces in STL files downloaded from 3D model web repositories. This happens because the STL format has been used in so many different tools over the years, and so many different contexts, and many of them don't strictly respect the rules of solid modeling. ASCII STL files can get large, but they are also human readable. If you open an ASCII STL in a text editor, you'll see a list of all the triangles and their three-dimensional coordinates clearly laid out. Binary STL files are somewhat smaller and more efficient. The format uses a single floating point variable to describe all of the attributes of each triangle. These files aren't human readable, and they come in a number of variant file types. There are some subsets of binary STL that incorporate color data, but these tend to be specific to an individual additive manufacturing suppliers rather than industry standard practice. STL is a widely understood format, supported across the CAD industry, and it's the universal import format for most additive manufacturing software. However, it should be considered an export file type. The triangulation required by the format makes it difficult to ever transform the design back into an editable body. Unfortunately, everything contained in an STL file is treated as a single rigid object by most software. So if you export an assembly as a single STL, it may not be possible to manipulate the individual parts of that assembly within your printer's software. In SolidWorks, we export an STL file by selecting the STL format from the available file types in the Save As menu. In this dialog box, we'll also find the Options button, which gives us access to the Preferences menu where we can manipulate the export settings. Let's take a few minutes to look at these settings over. The first choice is ASCII or binary. In general, I recommend you use binary. The files are smaller. Units lets you manipulate the unit size of the STL file, but the SBL format does not store this data inside of itself. So just remember that most printer software uses millimeters by default. Therefore, I recommend setting this to millimeters, regardless of your primary design units. Resolution lets you change the degree of smoothness in the triangulation of the exported part. Coarse can leave visible artifacts on parts with a lot of curvature. Fine can produce smooth surfaces at the price of a very high triangle count. Custom allows you to manipulate these settings for yourself. A quick word of warning here. While it's tempting to turn these settings up to the maximum in an attempt to get perfect output quality, remember that STL is a very inefficient file format. You'll quickly end up with a file that's hundreds of megabytes, even encoded as a binary STL. If your file climbs over 1 million faces, most 3D printer software will choke on it during processing. If your overall file size gets above 500 megabytes, many operating systems won't even be able to load it into memory for your printer's software to look at. The preview and show STL data functions will read out to you statistics of the created STL file and are great for giving you a warning that you're about to create one of those completely unusable monster STL files that we just talked about. The Do Not Translate option forces your model to be exported at the XYZ coordinates where it was created in SolidWorks. Typically, when an STL file is exported, all of its coordinates are automatically translated so that all the values are in positive space. Checking this box prevents this default transition from happening. But be warned, if you choose this route, it may cause your model to load into some very odd and hard to find location within your 3D printer's preview software. The Save All Components of the Assembly as a Single File option is fairly self-explanatory. If checked, it will create a single STL file from your assembly containing all of the components. If you uncheck this box, SolidWorks will save each component out as its own separate STL file. Sometimes this can be useful, saving each part of your assembly individually as a single operation. But more often than not, leaving this box checked leads to you accidentally creating 10 or 20 STL files that you didn't actually want. Check for interferences looks at your project as a whole and checks to see if it has parts that are overlapping or have a zero allowance condition. This can be really useful when you're exporting files that are meant to have free-moving internal structures, like if you're using soluble support material to print a live gearbox. Alright, now that we've looked over all the options, we're ready to export our study model in STL format. To use the STL format for this two-part overmold study, we'll have to export two separate STL files, then merge them together in Cura. We do this because if we export the design as a single STL file, both bodies would be treated as the same body, and we'd be unable to select and set each of these parts to their own material. To export only a single body from a component, select that body, or a face on it, before opening the Save As menu. After setting the export location, file naming, and okaying the file creation, you'll be asked if you wanted to export all bodies or just the selected body. Choose Selected Body. Repeat this for the inner part of the study model. With the two STL files created, import both into Cura. You'll immediately notice several things. First, the two parts aren't positioned in assembly correctly. Second, they're both set to be printed in the same material at the moment. And third, the parts aren't currently oriented for optimum printing. We'll correct these problems one at a time. First, let's set the material. You can change these material types independently by using these drop-down menus for each extruder. With the materials set, it's a simple matter of selecting each STL object, then clicking on the extruder that you'd like to use to print it. Next, we'll merge the two parts of the model together. Select both STL objects, then right-click to bring up Cura's context menu. At the bottom of the menu, you'll see the Merge Models option. Select it, and Cura will bring the two models together in reference to the original origin point from SolidWorks. Finally, with the models merged, we'll use Cura's standard manipulation tools to stand the parts up for an optimum printing orientation. We can preview our G-code by moving to the Layers view. Here, we can check that the model is going to print as expected before sending the job over to the Ultimaker 3. Now let's look at the 3MF format and how we'll export our part using it. The 3MF file format is a relatively new format specifically conceived for additive manufacturing. It was created in 2015 by a consortium of CAD software developers and 3D printer manufacturers, including Dassault Systems and Ultimaker. 3MF files are versatile containers that hold more than just a model's 3D geometry. The format has built-in support for elements like color and texture data, thumbnail images, printer settings data, and model versioning. A single 3MF file can contain multiple independent solid models, stored with their dependencies and relationships kept intact. While 3MF is still a triangulated mesh format, it has far more intelligence than the older STL format. 3MF supports advanced features like instancing, where one component of a model is used over and over throughout that model without redescribing it each time. It also does away with STL's old system of using a value to define the normal that determines the inside or outside of a face. In 3MF, an object is triangulated according to fill rules that determine the inside or outside of the object based on what order its elements have been written in. The basic export options of a 3MF file are very similar to that of an STL, with a few notable changes that we'll look at here. The Include Materials box will include the base materials of the model, body by body, in the output file. This allows you to include material properties in the data you send to your 3D printer, which can be used to drive manufacturing properties on some equipment. Include Appearances includes the surface's appearance of the part as a texture that's wrapped around the object. It's great for sending data to full-color 3D printers, but we won't be using it today on the Ultimaker 3. The advantage to a 3MF file is its ability to contain so much more useful descriptive data about a design than just its external geometry. The format is gaining support across the additive manufacturing industry, but hasn't yet reached the level of universal support that the STL file enjoys. So let's export our overmold study as a 3MF and see what happens. Inside Cura, we'll find the two parts are already correctly positioned and can be manipulated as one object using the transform tools. That brown bounding box around the object signifies that Cura sees this as a group of objects with their own internal relationships. To set the two parts of the model to print with different materials, hold down the Control key, or the Command key if you're using a Mac, and click on one of the subcomponents of the model. With it selected, click on the extruder that you'd like it to be printed with. Done. After a quick preview of our G-code, we're ready to print. A few other notes on manipulating 3MF files within Cura. If you'd like to break up a 3MF file inside of Cura, select Ungroup Model from the context menu. When you do this, all the parts will suddenly pop apart as Cura attempts to find space for each of them inside the build volume. You can stop this from happening by going to Cura's Preference menu and unchecking the Ensure Models are Kept Apart box. If you'd like to reassemble a part you've ungrouped, just duplicate the process we did with the multi-part STL file. Select each part in Cura, then use the Merge Models command from the context menu. Cura will reassemble the objects into their original configuration. Now let's look at our second study model. It's a simplified version of a continuous velocity, or CV joint, that was designed for a large 3D printed RC car. It has multiple internal parts that need to be printed in place with support material. We'll be using our Ultimaker 3's support material print core and water-soluble PVA to act as that supporting material. Before exporting the part in STL format, let's look over the options quickly. We'll want to export as a binary STL file, and we're going to want to make sure Save All Components of the Assembly as a single file has been checked. Otherwise, each and every ball bearing in this assembly will be exported as its own separate file. We're also going to want to activate Check for Interferences. As this is supposed to be a free moving part, when finished, any unexpected overlaps would keep it from working properly. The exported STL file is just over 14 megabytes. Loading it into Cura, we can see that this is quite a large part. I'm not going to make a full one-to-one prototype of this assembly. That will tie up my Ultimaker 3 for way too many hours. so we're going to reduce its size by 50%. When printing study models, always remember that volume equals time. The larger the volume of plastic in the part, the more time that part will take to print. A good rule of thumb is that doubling an object size will quadruple the amount of time needed to 3D print it. With our CV joint rescaled and reoriented, I'll set Cura to use water-soluble PVA in its second extruder. And then we'll set the software to automatically generate support material using that second extruder. After a moment, Cura is finished with its toolpath calculations. Now we can switch over to layer view and scrub through the individual layers to confirm that everything worked out as expected. Going back to SolidWorks, we can export that same CV study model in the 3MF file format. This time, the resulting file is only a little more than 3 megabytes. And this isn't really a terribly complex part, so it's easy to see how the efficiency of a 3MF file over an STL file would really start to add up when working with larger designs. Once again, in Cura, I'll reorient the part and shrink its size by 50%. That brown bounding box shows us that Cura has recognized this file as a group of bodies. If we wanted to, I could at this point control-click on each sub-object and change which extruder is going to print it. But for now, I'll just go through the same process of setting it up to be printed with water-soluble PVA support material on my Ultimaker 3. This session has been an introduction to the methods and file formats for moving multi-material objects from SolidWorks to a desktop 3D printing environment like Cura. If you have any further questions, please ask them in the comments below or check out our knowledge base at ultimaker.com.